We're recording. Say bye-bye to the doggies. Really funny thing. Bear's been like wild all morning and he has to like stay in my room. And so I put on a YouTube video of like compilation of dogs doing weird things, and he literally sits there and watches, and I'm like, okay. Alrighty, so some people said they had questions about chapter 14. So before we get into 15, please let me know any and all questions that you may have.
Okay, so I was doing the exam review handout, whatever he gave us, and it asked about set of resonance structures was the most acidic, and it had to do with like the reasoning had to do with aromaticity. So could you say that like if a molecule's aromatic, it's also acidic?
So, sort of, kind of, we're going to go into that acidity stuff in chapter 15. And it has to do with aromaticity, but it also has to do with the substituent groups. So you're on the right track, but there's a little bit more to it.
Okay, also, it asked about NMR stuff, like comparison, like when talking about aromaticity, and I even looked in his PowerPoints and I really didn't see much on it except that like if your chemical shift is a certain amount, it's aromatic or non-aromatic, whatever. But it also talked about let me look. It asked about draw in the protons on the skeleton provided, which are responsible for the NMR signal at 0 ppm, and explain why these protons have absorb at such a high field. So I wasn't really sure how to do that.
So we are kind of sort of going to talk about that, but you don't really need to worry about NMR in this chapter, because he likes to talk about it a little bit just because he really likes NMR, but he's not going to test you on NMR like drawing a structure or like reading the NMR spectrum, because that's not really what this chapter is about. There are like one or two little concepts that you have to know, which we'll cover probably today, but essentially you have to know that one, we talked about how benzene has completely delocalized electrons, right? And so that would then mean that all of the hydrogens are completely equal, right? Because they're all getting the same electron density. So that's one of the concepts. Every single hydrogen will be exactly the same because of complete delocalization. And the other stuff we'll cover when we get to it, just because I don't want to give you a lot of information without any background. Is that fair enough?
Yeah, I was just really confused why all this stuff was on the chapter 14 handout, not handout, the thing he gave us, because I didn't, barely even went over it, and then you haven't gone over it yet, so I just wasn't sure if that's something we should know right now.
Yeah, there's a lot of stuff in his chapter 14 stuff that don't really ever come up past his lectures, and he just talks about it because he liked it. So I don't usually tend to cover that stuff because it's kind of like extraneous information. You don't really need it. So you look it over, of course. I'm not going to say like completely ignore it, but it doesn't usually come up on exams or anything.
Okay, so even if it's like in the exam review packet, just kind of look over it, kind of understand it, but like a little, I'm not really sure.
Yeah, like I'll take a look at the exam review packet because I didn't see that he posted one. But
well, it's his chapter problems thing that he's already posted.
Oh, okay. Cool. So that's what we're talking about. Yes. For those, he always has questions that are not relevant which is annoying as heck, but he gives you a lot of different types of questions. I will actually go through because it's not fair for you guys to like have to pick out what's important. So I'll go through and highlight which questions you should be able to do, and then which ones are just like maybe like try for fun, and then which ones you absolutely don't have to know how to do, because there are a couple questions that students like flip out about because it's so weird and he's never covered it before.
Okay, thank you so much.
You're very welcome. Okay, and
I just have one other question.
yes, go ahead.
Is this the last chapter for aromaticity, or I guess the next one too? I'm just asking for the weekly assignments. Is like the EAS reactions coming up next, or is that like a while from now?
So that is actually what we're doing right now. So aromaticity, the chapter on aromaticity, it was chapter 14. This is kind of continuing that. So I like to put them in one section, sort of. So we're still talking about aromaticity, but this is the chapter on electrophilic aromatic substitutions, which is EAS reactions.
Okay. All right. Thank you.
You're very welcome. And then someone was asking about aniline. No, we haven't covered that yet. That's one of the common name versus IUPAC name stuff that we're going to cover. I don't know if we're going to do that today, but it's definitely part of chapter 15. And then someone said, is it normal to have only like 5 weekly assignments posted? I honestly don't know. This is the first semester that he's even doing weekly assignments. And I was a little bit shocked because I was like, wow, he's going to upload assignments every week. So I don't know if he's keeping that up or if that was just like for the first 5 weeks or what. And then someone said he's combining chapter 14 and 15 kind of in his lectures. Yeah, so this class tends to go in chunks. So like I don't like to think of them in chapters per se, especially in his online videos, because he doesn't do like a wonderful job of telling you when one chapter ends and when the other one begins, as you guys kind of saw in the chapter 11-12 section. So chapters 14 and 15 are kind of like that, where they build on each other. So chapter 14 just told you the basics of aromaticity, and then chapter 15 is building on those basics and then doing these substitution reactions. And then for exam 3 containing chapter 14, we should know mainly to tell whether it's aromatic, non-aromatic, and anti. Yes, exactly. So as far as chapter 14 goes, we will cover some practice problems, like exam-like practice problems, but essentially you just have to know whether something is aromatic, anti-aromatic, or not aromatic, and then you also should be able to answer basic questions about the molecular orbital theory for benzene and for cyclobutadiene. Also, if I sound kind of weird, I'm kind of sick today, but it's fine. Just don't judge me. Okay, so really, really great questions. I'm really happy again that you guys came in with so many questions. Anything else before we go into 15? And someone said he shouldn't call them weekly then. Yeah. Okay, it seems that you guys are good. I'm going to send the attendance thing one more time because I don't know if I sent it a second time. So there we go. And I actually went ahead and connected my iPad ahead of time and started sharing and recording ahead of time. So hopefully there won't be any issues. But of course, since I said that, there probably will be. But it's fine. So, as someone mentioned, this chapter is all about electrophilic aromatic substitutions, which I just call EAS reactions because it's a mouthful. And before we actually go into the... Someone said, girl, don't jinx it. I know, I'm sorry. Before we go into the actual reaction mechanisms and everything, we have to cover some conceptual stuff. So let's do that first. So we already talked about this a little bit, but how does the reactivity of benzene differ from other conjugated systems? So I'll change that to, are benzene rings more or less reactive than other conjugated systems that are not aromatic? And then while you guys answer that, someone asked, are we still going over chapter 14? No, just because of time constraints, I don't want to skip any of chapter 15. So the rest of those problems will be in the YouTube videos. And again, you guys answered for me in the chat. You guys are wonderful. I love it. Okay, so yes, you guys are correct. It is less reactive. And that is because it is more stable. You know what? I'll be more specific than that. Because aromatic is more stable. And this is like not something you guys should already automatically know, but in order to make benzene rings, which are usually unreactive, interact with a nucleophile or electrophile, when I say that, I'm essentially saying, how do I make an unreactive molecule reactive? And the way we are going to do that is with a catalyst. So what kind of catalysts do we usually use in organic chemistry? And really, really simple. Like, you don't have to give me super specific stuff, just in general. Acids. Cool, exactly. And what else? It's kind of like the opposite to an acid. And bases, exactly. So we can use acids or bases, but in this case, we are going to use acid catalysts. And there's going to be specific catalysts for each specific reaction, but we'll go into that as we do each specific reaction. So, true or false, I will have you guys answer this, and then I will explain it to you guys. So, aromatic rings only go through substitution reactions, not addition reactions. So, we haven't gone over it yet. I just want to know what you guys think. Wow, everyone said true. Cool. So yes, that is true. Aromatic rings only go through substitution, not addition. And we'll see in a moment the reason for that is addition reactions will get rid of aromaticity. And we never ever want to get rid of aromaticity if we can help it. And substitution reactions will keep aromaticity. So substitution reactions will keep aromaticity. Additions will ruin aromaticity. Stop. Anyway, I'm laughing at the chat. Don't worry about it. So, I've already given you guys the base of the reaction mechanism, and we are just going to go ahead and draw in some arrows. So, between A, B, and C, people are still laughing at what I said in the chat. So, whatever. I know I have a stutter. Rip Rosemary. Anyways, so between A, B, and C, which one of these do you think is the nucleophile? Yay! Yes, it is A, and that would be because of the extra electrons here, so the double bond will be able to attack, and we know that this would not be very good at that. So if A is the one attacking, and the arrow looks like this, which of these will be the electrophile? Awesome, yes, so Br2, aka B, will be the electrophile, but we have, before we can attack it, we're actually going to have an interaction between the acid catalyst and the electrophile. And I already ruined my next question, but C would be the acid catalyst. So this is kind of the super simple way that I will tell people to do it, like on the exam or whatever. But in reality, this reaction is a little bit more complicated. So I'm going to make an extra page here. And we're going to check this out. So benzene is super simple. He's just going to stay right here with its electrons, not really doing anything. But we have Br2. And we have our FeBr3. So FeBr3 is going to be our acid catalyst again, and it is going to kind of attack the Br2, and we get FeBr3 minus, and it is attached to Br, and that Br will have a plus, and it will be attached to another bromine. And so actually, I misspoke when I said Br2 is the electrophile. I got too ahead of myself. So FeBr3 is the acid catalyst, but if we're being technically correct, this is going to be the electrophile. So I'm sorry about my little mess up, but does this kind of make sense? So the acid catalyst must first react with Br2, and that creates the electrophile. And then now our benzene ring can then react with the electrophile. So now benzene is going to come in. I'm trying to figure out how to draw this without making it super, super ugly. But so benzene comes in, it attacks, seals that bromine, and so do you guys think it matters which double bond benzene uses to attack? No, and that's because, like we said, they're all the same. Exactly. So just for simplicity reasons, since I drew that double bond, that's the one that will say attacked. And it doesn't matter which side we add the bromine to, so I'm just going to pick here. So now bromine was added. We also have a hydrogen there, and we also have a hydrogen here. Those are implicit, so they're not usually drawn. But I'm drawing it now to kind of show you guys what's happening. So at this point, this is now just a regular old sp3 center, but this has a positive charge. And now we went from aromatic to what? Did we become non-aromatic or anti-aromatic? Non-aromatic, exactly, and that is because of this sp3 center. Cool. So now we are actually going to have this molecule come back again. And what happens is kind of complicated, where once this happens, this bromine at the end can now steal hydrogen, so kind of act as a base, and that will give the electrons back here to reform our double bond. And I'm sorry that this mechanism's kind of going everywhere. So now we have reformed the double bond. We still have a hydrogen here. And now we have, instead of a hydrogen, a bromine up here. And the other two double bonds stayed exactly the same. So at that point, we reformed aromaticity, or we recreated aromaticity, or you can even say we regained aromaticity. All pretty much means the same thing. So any questions so far about what I did? So someone said, so basically we have bromine act like a base in the second attack to maintain aromaticity. Exactly. So it's pretty much acting as a base, stealing the hydrogen and recreating aromaticity. And I'm trying to read the chat because someone said something earlier. I think it was a question. Okay, I don't see any questions, but someone did say we have the formation of the Iridium ion, and you are one step ahead of me. That's absolutely true. So this is the general mechanism that we're going to look at, and we're going to go ahead and name some important things in this mechanism. So this step where we went from the electrophile and the benzene ring to this molecule is the rate determining step. And the rate determining step just means that it is the slowest step and it requires the most energy. And so once we go through the rate determining step, we reach this thing, and this is the Iridium ion. And the Iridium ion looks different for each reaction that we're going to cover, but it basically has the same form of a plus here and a new group added here. And then someone asked, will the Iridium ion always be non-aromatic? Yes, because it's going to have that sp3 center and that positive charge. Exactly. Cool. I know I did a lot of zooming in and out, but just to go over it one more time, the benzene is the nucleophile. The acid catalyst is FeBr3. It's going to interact with Br2 in order to make the electrophile. And then the benzene attacks the electrophile, and we undergo the rate determining step, and we get the Iridium ion. And once we get the Iridium ion, the Br will act as a base and steal that hydrogen, and we will get this product, which is just a substituted benzene ring. And just so you guys know, we also get the byproduct HBr and FeBr3. Because once that Br steals the hydrogen, it separates and forms HBr, and we reform our acid catalyst. I know this is a new mechanism, so do you guys have any questions, comments, or concerns whatsoever? I'll give you guys like a second. If you do, is there a more stable product that forms? In this case, no. There's just going to be one product because the bromine is just, like, there's no other way for it to add. So this is the only product, but there are going to be a couple cases where there are, excuse me, where there are multiple products, and I will kind of like put an asterisk in what you guys know. Okay, so we went over the mechanism once. Now we are going to go to this table, and I'm essentially going to give you guys the painless version of this. Oh, actually, before I do that, someone made a very good point. So I didn't name this reaction. Move that down a little. This is an electrophilic aromatic substitution, aka an EAS reaction. And specifically, this mechanism is called a halogenation. So electrophilic aromatic substitution is the more broad name for all of these reactions. This one specifically is called a halogenation. Okay, cool. So going back up here, we're kind of... First, I'll actually answer this. Even though we answered it before, I'll just write it in the handout in case someone didn't get it. So the rate determining step is going to be the formation of the iridium ion, aka loss of aromaticity, aka the addition step. So all of these are referencing the same thing, but there are different ways that he can say this. And one more thing before we move on. So you guys know that the most general kind of reactions are addition, substitution, elimination, right? So substitution reactions are just when you do an addition and then an elimination, right? So most of you guys pretty much, like, that's obvious, it makes sense, right? So I had one professor who was really, really, really super strict and like weird about it. So just know that electrophilic aromatic substitutions are also called addition-elimination reactions. I've never seen Dr. West test like that, but it has come up when I've talked to him before. And this would be the addition step because you're adding the bromine. And then this second step would be the elimination step because you're getting rid of the hydrogen. Okay, so now let's really go into the fun part. So we are going to do 5 reactions in this chapter, but I'm going to try and make it as painless as possible because we are not going to sit here and do the mechanism for every single one. Yay! Instead, all you need to know is the reactants, the products, the reactants, the products, and the electrophiles. So I gave you guys a handy dandy little table here. So I'm not going to write, like, write it down in this table just because I need more space to write. But once I write the reactants and such, they're already listed here, so you can just write A or B, but I want to be more thorough. So I'm going to open up a new page here, and I'm going to recreate that table. And then someone asked, why was it elimination? So it would be considered an elimination in this step because we take the hydrogen and reform the double bond. So we got rid of this and created a double bond, so it's technically an elimination. But overall, it's a substitution reaction. So we have our handy-dandy benzene ring. And the first reaction that we already went over is the halogenation. So the halogenation can use any halogen as a reactant. So we're going to have X2, and X just means any halogen. And the acid catalyst will be FeX3. So most of the time it's going to be Br3, but theoretically we could substitute that for any halogen. And as we saw before, our final product is just our benzene ring with the halogen attached. The next one that we're going to do is a sulfonation reaction. And I will spell that for you. A sulfonation reaction. And the sulfonation uses SO3 and H2SO4. And you end up adding an SO3 group. And by the way, I'm just drawing the substituent on whatever side has the most space in the orientation that I've drawn it in. It could be anywhere on the ring. It doesn't matter. So that's fine. I actually didn't draw the electrophile for the halogenation because we already covered it, but I will do that just for completeness. So the electrophile is going to be X plus Fe X minus 3. For sulfonation, the electrophile is going to be SO minus H. Oh. And then someone asked, doesn't X on the far left have a permanent partial positive? So yes, both of them will, but just for the sake of kind of understanding how the mechanism goes, I only draw the positive here. But you were right, both of these would have a partial positive. Alrighty, so the next one we are going to go over is a nitration. So a nitration uses HNO3 and again H2SO4. So same acid, but instead we are going to get, sorry, this nitration is kind of obnoxious. So we get a benzene ring, and our substituent is just going to be NO2. And the electrophile Wow, I spelled that really wrong. Electrophile is going to be NO2. So N plus O2. So these three are the most straightforward ones. All you have to know is the reactants and the products. You don't really have to know the electrophiles. I just give them to you just in case, so you have some idea of how it works. He will try to trick you by giving you like SO3 with no H or NO2H or whatever, because this chapter doesn't have too much to trick you on. It's just knowing the reactants and the products. So just make sure you know that the reactant is SO3 and you add SO3H. And here the reactant is HNO3, but you only add NO2. All right, any questions on those three before we do the last two? Any questions at all? Okay, cool. So the last two reactions are kind of, they belong to the same group of reactions, which are called Friedel-Crafts reactions. So these Friedel-Crafts reactions are kind of special. They have some... Sorry, I got distracted. Someone asked, so those aren't EAS reactions? No. So all of these that we're covering are going to be electrophilic aromatic substitutions. But these are each kind of their own unique reaction under that EAS category. But the next two that we're going to do are both in the Friedel-Crafts category. But again, they're all under the EAS umbrella. So we are going to have a Friedel-Crafts alkylation. I don't know why that's so long. Friedel-Crafts alkylation and a Friedel-Crafts acylation. And just by the name alkylation, what do you guys think we're going to add to the benzene ring? Yes, alkyl group. Why did you do that? Exactly, an alkyl group. And someone said an alkyl halide. We're actually going to use an alkyl halide, yes. And then the acyl group, what do you guys think we're going to add for the acyl group? Oh, darn, I gave you guys the answer. So, yes, for the acylation, we will add an acyl group. My bad. My brain just shut off completely for a second. And now I'll draw that out to actually show you guys what I mean. So, the alkylation is going to be an alkyl halide. And very, 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 very important for you guys to know what's Friedel-Crafts and what's not. Both Friedel-Crafts reactions are going to use AlCl3 as the acid. So, alkyl halide plus AlCl3 equals alkylation. And we are going to end up with a benzene ring that has an R group on it. The kind of spicy part here is that the electrophile is going to be a carbocation. So it's going to be R plus, which is a carbocation. Sorry, I'm zooming in. Carbocation. And so if we have a carbocation intermediate, what do you think this means? What possibilities can we have? Rearrangements, exactly. So now we have the possibility of rearrangements or polysubstitutions. So let me write that down. Rearrangements and polysubstitutions. And we'll go into polysubstitutions a little bit more later, and I'll explain why that happens. Just for now, know that it's a thing. And that's pretty much it for the alkylation. Now we will go into the acylation. And acylation is going to use RCOX. And I'm giving it to you the condensed way because that's how Dr. West will often write it, but I will also draw it out for you. So RCOX equals R group, carbon, double bonded oxygen, and an X. And the final product will look like this. Double bond, did oxygen. And this is where students sometimes get confused because they don't remember which side you have to add to the ring. We are always going to get rid of the halogen side for Friedel-Crafts, and we're going to add the carbon side. So the R group stays and the halogen goes. Now, this is one example where the electrophile actually matters. So I don't know why my screen was bugging out a little bit. So the electrophile is going to be, as I said, we get rid of, sorry, this is really bothering me. I'm going to move the electrophile because I don't have enough space to up here, and I'm just going to move this little Friedel-Crafts thing here. So all I did was move the little Friedel-Crafts thing so I could encompass both of these, and I'm just going to move the electrophile up here so I have more space. All right, so the electrophile for acylation is just this. So we get rid of the halogen, but we can also draw it like this. And these are two resonance structures of the same thing. And does anyone happen to know what this is called? And then someone asked, is there an acid for the acylation? And someone answered, so thank you. I just forgot to draw it. It is AlCl3. So thank you very much. But do you guys happen to know what this is called? If not, that's completely okay. I'm just curious. Ooh, someone guessed tautomerization. Good guess, but that is going to be chapter 17. This is still considered, word. I lost it. It'll come back to me. Acyl cation, close. Yes, that's technically what it's called, but the name for this specific ion is going to be the Celium ion. It's a funny name, and it sounds kind of similar to our Iridium ion, so try not to get those confused. So I'm going to go up a little bit. Iridium ion is the benzene ring with the plus. A Celium ion is the electrophile for the acylation. So many people, someone said JK, lol. I know, everyone gets those confused. Don't feel bad if you get them confused. How I remember it is the Celium, acyl, and then Iridium aromatic. That's how I like to think of it. I don't know if that will help, but it helps me. So let's go back here, and I will zoom out. The big thing to note for both of the Friedel-Crafts reactions is that they will not happen when you have a strong deactivator or NH3 present. So I'm saying that now, but I will cover it again next session when we actually go over activators, deactivators, all that stuff. But I just want you guys to note, and I'll write it down here, that Friedel-Crafts will not happen with a strong deactivator or NH3 on the benzene. Right. And then I'm looking at the chat. So you can use either or as the electrophile. If so, how do you know which one to use? Great question. So when we're talking about the acylation, I don't know why I blanked so hard a second ago. So this is just called whatever. I'm just being stupid today. My brain is full of snot. It's what I was. Resonance. Resonance. All right, so this is just resonance because the electrons from this oxygen are going to come down and create that triple bond. And then these electrons from the triple bond will go to the oxygen to create this, right? So these are two ways to draw the same exact thing. So yes, both of them are completely equal. You can use either in the reaction. But he can ask you a couple questions about the Celium ion. So usually when we draw the reaction mechanism, we're going to use this version because one, it makes more sense because this is how it adds here. So that's just the more intuitive way to go about it. But also, let's call this A and let's call this B. Which one is the more stable resonance structure? B, exactly, and that is because oxygen is better at holding its charge. So this one is the one that we usually draw because it's more reactive, and this one is more stable because oxygen is holding the charge. So he could definitely ask you which of the following are resonance structures of the Celium ion. Both of these are correct. But if he asks you which of the following is the more stable resonance structure, this is the more stable one because the oxygen has the charge. And then someone asked, what is polysubstitution? We will go over that more next time, but essentially all it means is that in the case of Friedel-Crafts alkylation, once we add one R group, we're actually going to be more likely to go in and add more and more R groups. So instead of stopping here, we'll actually get multiple R groups on the ring. And then someone asked, which one is the more stable acylium ion and or resonance structure of the acylium ion. So I will just move this a little bit, and I will make a note underneath. So is the more stable structure. And that is because oxygen is holding the charge. And so I will zoom out in case anyone like wants to take a picture or anything, or miss something in the notes, or if you want to ask me any questions about anything. Cool. I don't see any other questions in the chat yet. So I'm going to send the thingy-majiggy one more time. And let's do a quick 1-minute summary. So again, in the reaction mechanism, the biggest things you have to know is that we have an acid catalyst that must react with whatever we're using here to make the electrophile. The addition step is the rate determining step because we lose aromaticity, and we create the iridium ion. And then we have to go through an elimination and get rid of the hydrogen in order to get back aromaticity. And then for each of these 5 reactions, all you really have to know is the reactants and the final products, and just have an idea of what the electrophile is. And that's pretty much it. Yes.
Is the addition step the rate determining step or the iridium ion?
I'm sorry, say that one more time.
Or both. Is the addition step the rate determining step, or is it when you make the iridium ion?
Both. So this step right here is the addition step. It's also the rate determining step, and it's also the formation of the iridium ion.
Okay.
Very good.
All right. Makes sense.
Cool.
Thank you.
You are very welcome. Have a great day, guys. You're very welcome.
Quick question before I go. For chapter 14, the SI, I was watching one of your videos, the ones that you recently just posted, and like it kind of cut off, and like I could only see your face for some of them, because I want to know if the benzene ring with 2 oxygens, why that was like non-aromatic, and I wanted to know like the benzene rings with there's 2 benzene rings with 2 nitrogens. You know what I mean? For the end of on the page 3.
Okay, so for some reason my screen stopped working and it refused to reconnect, so I had to do it on the board. I think that's what you're talking about.
Yeah. Oh, so you did it on the board.
Yeah, it's really hard to see, I know. So I will make sure by the end of this week to post like a tutorial, whatever you want to call it, on YouTube of just me doing the examples, and I'll cover all of them. I can specifically show you those ones in SI or in tutoring if you want, just so you don't have to wait. But I will for sure upload that this week.
Yeah, I signed up for the one at 1.
Okay, perfect. So just remind me and we can go.
Thank you.
You're very welcome.
I'll see you there.
Bye.
Quick question.
Yes.
I know this is 100% my problem and not yours at all, but I came in late today. So when would I reasonably expect this video to be posted on the YouTube channel?
I will post it right now because I have an hour until my tutoring starts, so I will go ahead and post it right now.
Okay.
Also, don't ever feel bad. You're welcome. Don't ever feel bad for coming in late. Everyone has a life. Don't worry about it.
Right. Okay. Enjoy your day.
Thank you. You too. Bye-bye.